Hey YouTube, just want to do a video explaining my efficient use of solar panels to extend EV range. So I added solar panels to my electric car. So I got a old Gen 1 Chevy Volt 2013. It's basically an electric car that has a generator that can drive it around once the EV battery runs down, and you can plug it in to charge it back up. So the solar panels, everyone who buys electric cars, at one point in time you're thinking, how can I extend the range with solar panels? So just want to explain some of the mods I made to basically make this whole thing work. So just a quick note, this is an unscripted video and I'm going to try and do it in one take. So solar powered cars, not a new idea. There was some attempts back in like the 1950s. So it's like an 80-year-old concept by now. You've got the Lightyear one, which is I think a Dutch company that went out of business recently, and then there's Aptera, which is seemingly always on the verge of bankruptcy and never in production, but I really hope they eventually do make their car. But in terms of actually adding solar to like a car with a high voltage battery, it's not a new idea. I mean, the second or third gen Priuses had a solar roof option that you could buy, and it basically help run low voltage loads. There's a lot of criticism about it, like it only ran a fan or something like that. It only helped the climate system, but I hope to explain kind of my mods and how I feel like what I was able to do, kind of combining a bunch of different modifications together. I feel like it made the most simplest, most efficient use of solar panels to both improve the electric vehicle range and essentially reduce fuel consumption, right? That's the end goal. This would also work in like a internal combustion car or just like a regular plug-in hybrid, not a EV, but yeah. So challenges whenever you talk about adding solar panels to electric cars, there's a lot of naysayers. They want to point out everything wrong with the idea, and I hope to basically just start this presentation with addressing a lot of the main complaints here, and then also some things that people don't really think about because they've never actually tried to do what they're criticizing, right? So challenges that I felt like needed to be addressed: limited availability of solar energy. There's only so much irradiance per square meter. There's only so much sunshine. A lot of systems, they have an aerodynamic drag or weight penalty. That's important to take into account. And then what's not always talked about is the difference between like solar panel voltage and then the voltage that the car's electric system uses, the traction battery, the thing that propels you down the road, the high voltage battery. Also, no one really seems to talk about heat very much, which I think is super important if you're going to be parking in the sun more often. And then practicality or usability, like, is this something that I can use while I'm driving down the road, or do I have to, stop and plug it in, or, how does it actually work? And then it's also important to remember panel cost and durability. Are we making a trade-off by somehow, the way that we route things? Are we using some of the components? Are they going to wear out sooner? I think that's important to address. And then also just the overall complexity and reliability of the design. Is the design so complex that you need an engineering degree? Well, I don't have one, so I feel like I was able to figure it out with kind of a more analog, dumb approach, right? But it's just a picture of the 1987 Sun Racer. I remember reading about this car when I was like in 4th grade, and I was like, wait a minute, cars can run on solar power? I thought this was the coolest thing ever. But wow, it was like 40 years ago. So limited solar availability. There's an interview with Elon Musk talking to Joe Rogan, I think like in 2021, and basically he does the math right, but I feel like he comes kind of to the wrong conclusion. So there's only about 1 kilowatt of solar power per square meter. Don't really know what a square meter is, but I've seen a bunch of buildings being built and they've got these like 4x8 sheets of plywood on the roofs, right, for sheathing. And basically each one of these 4x8 sheets is about 2.5 meters, and is also about like the practical limit of what I think you could theoretically add to a car in terms of solar power, right? if you think about driving around with a big sheet of plywood on your car, that's probably about the limit of in terms of like total area that you could ever point towards the sun. But you do the math, so these are in units, so-called sun hours. So it's like a national average of how much sun they get, or total hours of full sunlight, right? So in different parts of the United States, somewhere between like 4 and 6 total hours of sun. So this left column would be like in the winter, and this right column would be like in the summer. So, you know, areas like California get a bunch of sun pretty much all year round. And then other areas like in, Maine, they don't get very much sun in the winter, and they get only a little bit in the summer, unfortunately. But, you do the math, right? So let's just call it 4 hours of sun hours per day, right? And then with a 25% efficiency, so you multiply those together and you get a value of 1. And then total square footage, or square meterage, or whatever it's called, you get about 2.5 kilowatts max on a car. You run that through a typical efficiency of like 4 miles per kilowatt hour. And Musk's right about the math. It is about 10 miles per day, best case scenario. But you got all these losses you got to account for too. And then but I still think that this is a pretty usable 10 miles of range per day. I mean, most people only drive 30 miles to work, right? So I guess to work and back. So in terms of aerodynamic drag and weight, so there's been a few YouTubers that have put out some pretty cool mods. There's this channel called Real Solar Cars on YouTube. A guy, I think his name is James. He's an electrical engineer, and he basically has this really slick system where he put like 2 full-size panels on his car and basically did everything correctly. At one point he did kind of say that there is an aerodynamic weight penalty. So on the highway, he said he's getting somewhere around, he loses about the same that he gains. It's like a net wash. But most of the city driving works out fine, where he's able to charge a lot on solar power alone. But it's also worth taking into account the mounting solution, right? Like the weight of all this stuff, it all adds up. And then how do solar panels actually work? You got these thin little wafers of silicon that each produce about 0.5 volt each, and then they're all wired in series, and that's how you get a usable voltage out. Like, what are you going to do with 0.5 volt? So you wire all these in series, and then it comes out to somewhere around, there's like 12 volt solar panels, or 24 volt, but they're actually a little bit higher. You need a higher voltage to charge a battery, and then you also, depending on how much sun you're getting, these produce a variable amount of voltage. So the issue is most solar panels, 12, 24, 48 volt. There might be some that are a little higher. They're a ways away from what an actual electric vehicle high voltage battery is. If you look at the old Priuses, or a lot of the cars from Japan at that time, they're around 200 volts on the NiCad chemistry batteries. They had at least 168 cells in series in order to get that. But with some of the newer lithium chemistries, like Tesla Model 3 and Model Y, which is basically just a Model 3, in the US, almost all of them are this NCM, or nickel, cobalt, manganese. They have at least 96 cells in series, a bunch in parallel, and it's about a 400 volt architecture. It'll go between like 350 and 405 volts or something like that. But for those in the know, they also remember that Tesla used to sell the Chinese kind of battery pack here, which was based on the LFP, or lithium iron phosphate chemistry. Those packs actually had slightly lower voltage. They're a lot more stable over that usage range, but it's kind of an outlier, but slightly lower voltage. And then there's the Chevy Volt. Is also a 400 volt architecture. I think it's LMO instead of NMC. It's just an older chemistry of essentially the same thing. And then you've got some of the newer cars, like the Taycan, the Porsche Taycan. I think it was an 800 volt architecture, somewhere around there. But you see, there's a large difference between like the voltage that a lot of solar panels put out versus what we need to get either into the battery or out of the battery. So that's a big issue. And then heat. If anyone grew up owning an Xbox 360 and was unfortunate enough to have it, red ring of death on you, you learn the hard way that parts of electronics don't like being exposed to large amounts of heat for extended periods of time. And there's these components, they're called capacitors. They're kind of like really small batteries that are really efficient in terms of like storing and releasing charge, but they've got this electrolyte in them, and that can either leak out the top, or there can be internal structural issues with the heat. And that's just to say that heat generally accelerates chemical reactions of any type, exponentially. So this is an issue. Parking in the sun will inherently accelerate wear and tear on a car. So something to keep in mind. And then practicality, usability. Really like Beat the Bushes channel. He did a funny video once where he put a bunch of these portable solar panels on his Tesla and had it running into an EcoFlow system that was like charging his car on like a kind of like a trickle charger, like a few miles an hour. But if you think about like practicality of putting these portable panels on your car, that's something you have to get out and do, and then you have to plug it in somehow, and then you also have to worry about them getting stolen or vandalized. There's this new product by Ghost Sun. They're on YouTube. They've kind of got this other system that they both basically had to add this like buffer battery somehow in order to get a usable amount of capacity to use the onboard charger. And then the other issue is if you are thinking of doing something like this, you got to get the wires in, and you need this wire to go through the roof. You're talking about a roof penetration, so that's important to consider. Panel cost nowadays is not that big of an issue. Solar panels are pretty cheap. There's really like 3 types of solar panels that you can buy. There used to be like amorphous and polysilicon. Those are pretty much not available anymore. They're just not feasible to produce nowadays. By far, the vast majority of solar panels are going to be like a glass type. What are they called? Monosilicon. So it's like one individual wafer that this is cut from, or one crystal, I suppose. And then flexible are basically the same ones, but they're a lot thinner, and they're mounted to like fiberglass or some kind of semi-flexible backing. And that's not to say that they actually are flexible. So flexible solar panels, they're mostly just flexible in terms of when you install them. They, if you think about tiny sheets of glass, they can get cracked and damaged. And these little wires that bond everything together can either come off or corrode if there's oxidation in there, or even just the small micro cracks that can form. The panels can get hot, and then it's trying to run electricity through a gap. It can cause accelerated degradation. There were these truly flexible solar panels called CIGS. They used, I think, an organic like a dye or a pigment, and they're really cool. But they with all like pigments, you think of like a house that's painted, like the paint fades, right? And the problem with these SIGS panels, or whatever they're called, you only got like 5 years of good solar production out of them before the pigment started to not work, and then per square area they weren't as efficient either. But and then just as like complexity and reliability, I'm not as smart as this guy that did the whole Real Solar Cars YouTube channel. He's like a proper electrical engineer, and he actually figured out how to practically mount like a custom high voltage inverter board, and then he wired it into the high voltage battery. It's like really efficient the way he did everything. And then he also optimized the contactors. That'll come up later. I'll explain those. And he was also able to, I guess, he used the CAN bus as the language that cars talk nowadays, and he used like a Raspberry Pi. But you're talking about 2 coding languages I don't know how to use, and then all this electrical engineering stuff. It's kind of over my head, but it's worth checking them out if you want to see another way to do this. So it's worth kind of just reviewing how electric vehicles kind of like use and move energy around. So electric vehicles are just like gas-powered cars in that they have a traditional lead-acid battery, and the lead-acid battery, it's always connected to the car. When you turn the car on, that's the first thing you're interfacing with, and it essentially isolates the high voltage battery through these big, contactors that disconnect. So there's no chance of like getting electrocuted when the car's not on. So most low voltage batteries, they're called, because it's a typical like 12 volt car battery, they're just lead acid, just like internal combustion engine cars. And then the high voltage, or what's also called the traction battery, because it sends power to the wheels, usually through an inverter. Sometimes, almost all electric vehicles, they also have some select modules that they also power. So like in the Chevy Volt, that would be not just the inverter and motor, but it's also the air conditioning is a high voltage component. There's another one called the accessory power module, which is essentially the alternator for an electric car. It doesn't actually generate power, it just kind of converts it from the high voltage battery down to the low voltage battery. And then there's a few like super high draw items like the cabin heater in the Chevy Volt that uses a PTC element. It's kind of like a space heater, but it uses high voltage. And it's just much more efficient to use high voltage to do that, because it's, at least in the Chevy Volt, it's directly heating up like a glycol ethylene, the coolant that it moves throughout the car. I guess technically the onboard charger is a high voltage component, but as far as the accessory power module, so that's a kind of an interesting component. In the Chevy Volt, they put it under the trunk and the subfloor in the back of the car, and it's right next to the lead acid battery back there. So with 12 volt, you lose voltage pretty easily in terms of distance, so it makes sense that they're right next to each other. And it's essentially acts as like the vehicle's alternator, and it steps down that high voltage somewhere around 400 volts down to somewhere around 12 volts DC. Now with this component, GM had to engineer it to a certain efficiency over a certain like current. So you'll see that it's really made to be most efficient when it's putting out 50 amps of like 12 volts and then higher current. That's when it's at that 90% conversion efficiency of stepping down the voltage. But at these lower voltages or lower currents, its efficiency really drops off. So the strategy that GM took was to basically have the accessory power module go to sleep, so to speak, when the 12 volt battery by itself could handle the loads. The way that it does that, so I guess just in a sense is just trying to maintain that 12 volt battery. If you put a voltmeter on the Chevy Volt, you'll typically see somewhere around 13.5, 14.5 volts when it's driving. Now what's actually happening is it's going between these different modes of operation. So there's what the GM calls the normal mode, which it's basically trying to get that voltage above 14 volts. And then if you turn the headlights on or a high load, then it says, well, maybe we need to target something like 14.5 as if we're a regular alternator. Most alternators at least will charge to like 14.5, maybe 15 volts sometimes. But there are these two modes. So one of them is called fuel economy mode. And so what it basically tries to do is, if you're barely using the low voltage battery or low voltage system, it'll just turn off until the battery comes down to like 12.6 volts, and then it'll turn back on. So that basically allows you to stay on this side of the curve more often, even though there's losses going into the 12 volt battery when you're charging it up. It's less than the losses that you would get if this component was on all the time, like essentially trickle charging the lead acid battery. And then there's what's called a voltage reduction mode. I understand that more so as like a over voltage mode, where it just needs to get the voltage down, because sometimes lead acid batteries drop a cell and then they can do weird stuff. But important for designing a system is this kind of secret mode called desulfation. So a lot of people know that you can recover a lead acid battery if it's dead by essentially overcharging it somehow. So in the Chevy Volt, about once every week, maybe once every 2 weeks, it'll try to charge the battery up to essentially overcharge it to like 15.5 volts for a few minutes. Jim's not really clear on how long, but this higher voltage range is kind of important to know if we're going to be modifying the low voltage system, because I'm not smart enough to trick the car to not do that, so I don't want it to like overcharge lithium batteries. I heard that can be dangerous. So what's my solution? Basically, it was important that I felt it was important to flush mount my solar panels. So I went with these flexible 200 watt panels. So 100 watts, and that way it just really minimizes the aerodynamic drag that kind of conform to the shape of the vehicle. Instead of drilling an extra hole in the roof, I repurposed the antenna penetration. It's kind of hard to see, but actually I was able to find like a cable cover for a marine boat or something, and it's actually lower profile than the original antenna that used to stick out. So maybe it's a little bit more aerodynamic. Who knows? And then what's also important is, for my system, the most efficient use of solar panels on a car is to have an adjustable MPPT charge controller. There's two types. There's PWM and then MPPT. And not going to get into the nuances between the two, but the PWM essentially just changes the duty cycle of how long the solar panels can try to charge something. And MPPT has a true inverter or a transformer inside, like a big chunk of copper, wound around as a coil. And it can essentially take a voltage coming in and it can change it to a different voltage going out. And a lot of those have an adjustable mode where you can basically select the voltage coming out, and you can fine tune what you want the charge controller to charge at. And it's a true voltage, it's not a target voltage. So that really opens up the world as to like modifications and stuff. And so also really important to getting this system to work and produce the most amount of energy, most amount of times with minimum amount of input, is to get rid of the lead acid battery, the AGM battery. Lead acid batteries, they're really heavy. AGM's a little bit better, but ideally I wanted to go with a chemistry that stored significant energy at a higher voltage, essentially above the range that the accessory power module was going to try to charge at. Give me that like some overhead buffer where I could continue to put power in even though the car was like, I'm full. I can still keep putting solar power in, either if the car's on or off. That's kind of the secret sauce, so to speak. Big thing for this, whatever chemistry I was going to go with, it was important that I didn't have a thermal management system. Like a lead acid battery doesn't need a heater, right? Unless you live in like, I don't know, Fairbanks, Alaska or something. That's really important. We'll come back to that. So you might be thinking, well, where does the EV range actually come from, right? I'm not putting any electricity into the high voltage battery, but I suppose you could answer that with an analogy, right? So money's really easy to comprehend for a lot of people. So if you had two people, person A, person B, same job, same income. Person A, he says, I'm going to work an extra overtime shift, once a week, and I'm going to make an extra $100 a week. And then person B says, I'm going to spend the same amount of money and everything, but I'm not going to work any overtime. Instead, I'm just going to save $100 a week. Maybe I buy cheaper groceries somewhere or do something. If you were to come back to these people in like 5-10 years, which one would be richer? I think it's actually, in today's society, it'd be person B, because you've got income tax, capital gains tax, you've got property tax, you've got all these things that they all feed into making it more efficient to save money versus to earn money. The same is kind of true for a high voltage electric battery in a car. So we've got power coming out that we're spending through this. This is the APM, the alternator, and then that's going into the low voltage battery. Now I could put electricity into the battery. This is what people usually think of as like charging your car with solar, or maybe it's more efficient to just put that 12 volt power into the low voltage battery instead. And then we're skipping that, a lot of the losses in this whole system. But, how much power is actually used by the 12 volt system? Is this like a minimal amount? Is it even worth considering? So I added up all the 12 volt components I could think of on the Chevy Volt. And then above this line is basically everything that is not optional. And then below the line is everything that is optional. And you see, at all times you're using almost 300 watts, especially if you're driving at night. The headlights and the daytime running lights, they're almost using 200 watts by themselves. The high voltage contactors, they always have to be held shut, even though they have economizers in the battery. So those are always going to burn some amount of power, and then you got to power like the infotainment system and whatnot. And I was actually surprised to find like the HVAC, like the cabin fan, almost uses 300 watts. And some of these components, like the rear defrost, that thing's like a third of a space heater. I didn't realize it just, blasts. I guess it makes sense because it defrosts the windshield so quickly, but potentially you're looking upwards of 1.5 kilowatts going through the 12 volt system, especially in the winter. You're going to be using a lot more of these systems. So just something to think about. It's not, I think a lot of people think that the low voltage system kind of uses a de minimis or less, it's not even worth considering amount of electricity. But it actually does. And then it does use a lot. And then especially if the car is sitting for a long time, it's got to run like pumps and stuff to keep the high voltage battery. So it's never really turned off. It's always kind of running in the background. The computer's waking up. So it's not just when you're driving either. It's when the car is sitting in a parking lot, it's still using some 12 volt power. It's also worth kind of taking into account AGM batteries are heavy. The one in the Chevy Volt's like 40-50 pounds. And then if you did replace the lead acid battery with something a bit more efficient, you'd have a lower internal resistance of the low voltage battery. So essentially that would be like the tax you have to pay whenever you charge that 12 volt battery up. It's going to be lower with like a lithium chemistry, for example. And then there is this kind of weird problem with lead acid batteries where they have this voltage sag. It's like the voltage gets squishy. So like there's nothing really there. When you have to charge a lead acid battery above what it normally operates at significantly. And whenever you turn the car off or stop charging it, the battery kind of squishes back down. It's not really losing capacity. It's just, it was that voltage to begin with. You just couldn't tell. And then the car is also, whenever you turn the car on, it has to check to see, is the AGM battery or lead acid battery, is it fully charged? So what does it have to do? It has to first start charging that battery and then check. So if we could get rid of that voltage sag each time we turn the car on, the APM would spend less time charging it. There is technically a self-discharge of lead acid batteries. For a new one, it's like 1 or 2% per month. But with an old one, it could be 5% a week, 10% a week if it's really old. So you park your car at the airport, go on a vacation, come back a week or two later, you could be losing a significant amount of power by the time you use your car again. Especially retired people, they don't drive very much. And then there's something engineers call V squared over R losses. It's essentially how much does a wire heat up when you run electricity through it. And the higher the voltage, exponentially you lose much less energy due to heat. It's actually more than technically V squared R. That's just kind of like the term they use. So the efficiency loss is proportional to the square of the voltage. So if the voltage were to double, you wouldn't use half the current, you'd use a quarter of the current, because it's 2 squared, not 2 times 2, if you follow me. But it's actually a little bit more than that, because when wires heat up, they also gain more resistance. So it's not just the voltage, it's your voltage plus how hot the wire is. So it's a little bit more than that, but it comes out to be potentially up to a third with the modification I did when the working at the voltage that it works at. And then all this is to say that basically we're increasing the amount of time that the accessory power module is asleep. And then potentially you're saving up to 30% there, just based off how efficient the APM is. And something I thought was interesting is there's this out-of-spec bits interview with this, I think is a GM engineer, someone that he did a 1,000-mile road test on a single charge of the new Silverado EV. And something that none of the articles pointed out, but he did mention in the interview, is that whenever they were between shifts, you know, because they had like an army of like 100 people drive this thing around for forever, whenever they were between shifts, they put a 12-volt battery tender, which is a 12-volt battery charger, on the car. Now, it's not sending power back in, but you know, potentially this, at least in this case where they're driving really slow over a very long time, that added a huge amount of effective range to the car. It's just something worth considering. And then, you know, this begs the question, why not just feed power directly into the traction battery? So there's what I call the high voltage tax. So whenever you energize the high voltage system, you're taking power in or you're taking power out, you have to pay the high voltage contactor tax. It's about 15 watts when they're running. But if that high voltage battery is connected to anything, you're always paying that 15 watts. And then in order to get from the solar panel voltage of what's typical up to the high voltage battery voltage, you're paying another, you know, at least 15% loss from an inverter. And then that is to say you're doing all this to add electricity into the high voltage battery just so that when you drive the car later, it can come back out and you'll pay another 10% tax going through the APM to recharge the 12-volt system. You would have avoided all of these if you would have just went into the low voltage system to begin with. It's worth thinking about. This is a really cool idea, but a bad idea is just using the onboard charger more often. I mean, it needs at least like 100, 200 watts in order to energize, because that's what the charging protocol is based on, is like these kind of higher power loads. And so like if a cloud is going over, you know, and the high voltage contactors are closing and opening, you're going to start wearing components out. The way they get around this apparently is with a lithium iron phosphate battery in this compartment up here. It kind of acts as like a buffer, so if there's like a cloud that goes over, it doesn't have to stop charging. But you're still, you know, you're causing wear and tear on these high voltage battery components. And it's not just that. I mean, you're also plugging this thing in, so like the plug is, you know, getting a lot more wear. And these contactors, truly they're safety items, and you're putting a lot more stress on them. Not to mention, you know, if you're directly wiring high voltage somehow from up here down into the battery, then high voltage wires are kind of dangerous. Electricity likes to get out of them. So it's worth pointing out these state of charge to voltage charts you can find online. They're all estimations. All batteries kind of have this kind of ambiguous voltage to state of charge curve, and it depends on how much energy you're taking out at once, or if the battery was just charged or is being charged. So these are not scripture, so to speak, but just know that like an AGM battery is the most common versus the most common 12-volt quote-unquote lithium battery. They line up pretty well, but there's this issue that happens with LFP that's very important. Essentially, you'll damage an LFP battery if it's ever charged above 15 volts. The thing is, it's inherently normal to charge a lead acid battery at 15 volts. Maybe not normal, but a lot of cars do it. The Chevy Volt goes to 15.5 in the desulfation mode. So that right there can cause some problems down the road. And then the other big thing is LFP it's just damaged if it's charged below freezing. So yeah, you know, cars exist in freezing weather. So either you're going to be paying another tax to run a heater all the time if it's in freezing weather, or you're going to destroy the battery in a short amount of time. So these are very important considerations. As far as other chemistries, so we've got LFP, we talked about that one. These are on a per cell basis. So LFP somewhere between like 3 and 3.7 volts, but around 3.4 volts when you're pulling energy out of it. There's also NMC, which I introduced earlier. That's like the battery in your phone, the battery in most electric cars. That one's between 3.5 to 4.2 volts is where you can normally take energy in and take it out and not destroy the battery. And then there's the new kid on the block, the sodium-ion battery. These are really cool because they have a lot of similar characteristics in terms of like operating temperature as lead acid, but they're still kind of expensive for what you get. And the big issue with these is they have a huge change in voltage over their available state of charge. Yeah, it's great that you can discharge them all the way to zero essentially and not damage them, but most automotive components are not made to operate at like 1 or 2 volts. You know, you can't really go below what you would expect with lead acid. So you leave a lot on the table, almost 50% when you really do the math as to like how many, if you use 4 cells in order to get a workable voltage range, you end up leaving almost half of the energy density on the table. Now there is this chemistry called LTO. That's the one in red. That one's really interesting because, as I understand, it's the only chemistry up here that's actually named after the anode. So all these are named after cathode materials. That's the positive pole of the battery. NMC, LFP, sodium. LTO, as I understand, they're usually NMC batteries. That's how they start out. And then they take the anode, which is carbon for all of these, and they add a titanium oxide coating. Now that kind of ruins the voltage that you get out of it because now you have to discharge through this titanium oxide layer, but essentially it makes the anode like impervious. And so the anode doesn't, change shape. There's all these aging mechanisms of batteries that have to do with the anode. And when you coat the carbon in titanate oxide, then you essentially make it bulletproof. And it just so happens that when you do that to the NMC chemistry, the voltages now in a 5 and 6 cell series, they actually line up a lot better in terms of state of charge and automotive applications. Particularly the LTO and the 6 cell series, you can get almost 90-95% of the total capacity and still be in the expected operating range of a lead acid battery. So that's really interesting. Actually, the mining industry, I heard, is starting to use a lot of them just because they're so bulletproof. And people don't realize lead acid batteries are freaking dangerous, especially when you start wiring them in series like they do for industrial equipment. They have a tendency to just like randomly explode and throw acid everywhere. So I guess LTO is pretty interchangeable and a lot safer for some applications. It's worth just kind of contrasting these two, since in my view these are kind of the two viable chemistries that have been demonstrated. So both LTO and sodium ion, they're both ultra temperature resilient. So we're talking you can charge them down to -40 Celsius or -40 Fahrenheit. That's like, those are like North Pole temperatures. That's crazy chilly. People don't really live in areas that get that cold, so they're pretty much interchangeable. And I'm pretty sure lead acid, those batteries, even if they're charged, they freeze, if you go to the Arctic Circle. So you're not really taking a hit in terms of temperature usability. And then in terms of life cycles, so at least in the lab, so sodium ion is pretty new, but apparently LTO is like, it has like 10 or 20 times as many cycle lives as sodium ion. It's like, it just goes forever. In terms of lab cycles of aging, NMC, I want to say lab data says it's like around 1,000, and then you've got LFP, which is like, what do they say, like 2,000-3,000 in the lab. And then you've got sodium ion, which is maybe a little bit better, like 5,000. LTO is like 10, 20, 30,000. Like, these things are just bulletproof. And when they do age, they don't lose capacity as quickly. So really interesting chemistry. Super resilient to high cycle life. And then both of them are kind of over discharge resilient. So like, you leave your headlights on and the car battery drains to 0 volts. I mean, that thing's dead if it's a lead acid battery. Sodium ion doesn't care. You can lower all the way down to 0 volts. LTO, as long as you don't go under like a volt per cell, right? As long as the car battery isn't drained past like 6 volts, it's still going to be totally recoverable in terms of capacity. Now, most cars, like if you somehow did over discharge the battery, a lot of them have systems where they basically force all the computers and stuff to shut down. They're not going to run at like 6 volts. So it's not as big of an issue, for in a real world application. They both essentially have the same over discharge resiliency. And then in terms of price, right now they're about equal, ironically. In the future, I'm sure sodium is going to continue to get cheaper. I mean, sodium inherently is just cheaper than titanium, last I checked. And then there's no real traditional BMSs for these types of batteries. What everyone's been doing is they've just been using active balancers, and this includes commercial solutions. If you buy a sodium ion battery on Amazon or whatever, it's going to come with an active balancer instead of a BMS. And then that's actually really good for automotive application, because you're essentially mimicking the properties of a lead acid battery. Lead acid battery, there's nothing to disconnect the battery if something goes wrong, right? That's why you've got fuses. A BMS, the way I think of a traditional BMS is it's something that stands in between the battery and the load. And if there's a weird condition, if there's a high voltage, over discharge, if it's too cold outside, or it's like a Wednesday, it'll disconnect and leave you stranded. You don't want that in an automotive application. Like, sometimes you gotta get home. So an active balancer is something that it doesn't sit between the two, it sits on the side. And all it is there to do is to make sure that the cells are equally balanced. And then, I think I said this, sodium ion, about 50% usable in automotive application. LTO, somewhere around 90%. Safety hasn't really been demonstrated with these chemistries, like head-to-head, plus sodium's so new, but they're about equal. Actually, you can approximate battery chemistry safety based off of typical cell voltage. The higher the voltage of a cell, the more inherently dangerous it is, because typically higher voltage cells tend to have more energy density. And more energy density just means that there's more energy to release if something like a nail goes through a battery. And so sodium ion is actually potentially less safe with that calculation compared to LTO. Now, apparently what really matters when you start getting in these chemistries is off-gassing. I don't know that that's been demonstrated with either of these two chemistries, but yeah. So as far as the active balancers, these are very misunderstood on YouTube. There's a bunch of videos on YouTube that basically explain them as if they're like these items for people in third world countries to use salvage old lithium cells and make usable lithium battery banks. I mean, they'll work for that. That's not what they're for. They're really meant to be like a dumb BMS that sits on the side and is always trying to balance the cells. Now, a traditional BMS, it's only going to try to balance cells when you're like at the end of the charging curve, so a very small amount of time. So in some cases, they're balancing more often. Now, they're also able to balance with a lot more authority, if you will. They can, and they're also a lot more efficient when they balance. The problem is they have to sense a voltage imbalance before they can start affecting the balance, if that makes sense. So like capacitive active balancers and inductive active balancers, there's really only two types. capacitive ones, they can usually balance everything within like 0.1 volts. But inductive active balancers, they usually wait for 0.2, maybe 0.3 volts before they actually turn on and start balancing and reducing that difference. So potentially that might be too late for some applications. But the thing is, inductive, I mean, those things are bulletproof. Excuse me, they've got like no self-discharge. They don't really parasitically draw anything. Like capacitors, they're always like bleeding static charge out. And capacitors, they're always the thing that goes wrong. But the inductive ones, they can take crazy overcurrents and not burn out. They're usually cheaper than the capacitive ones. But just kind of different strokes for different folks, I guess. With LTO, I think you really want to use a capacitive active balancer. I didn't, but yeah. So in terms of the actual charge controller, I think I explained this okay earlier. Most MPPT charge controllers nowadays, they'll allow you to set that voltage in like specifically, exactly when to turn on, when to turn off. But now, just in terms of, because I know solar panels are usually a typical voltage, and I know that there's a typical area that they can occupy on a car, I can say with a lot of confidence that a 20 amp MPPT, it can probably work depending on, how many solar panels you're putting on. It's almost always going to work. A 30 amp, that really should work. Now if it's capable of doing 40 amp, I mean, unless it's like a big truck or something, it's going to be overkill. The problem is when you're talking about these higher currents, you're now talking about a bigger transformer that has to be wound in these, so the prices go up dramatically. So 20 amp, I mean, these used to be like $10-15, now they're like $40. Thanks, Biden. And then the 30 and 40 amps, those are like double and triple, so they can get expensive. There's these super cheap ones. They all try to hide the fact that they're PWM ones. You can tell them just by looking at them. Like, if they look like any of these, they're PWM ones. If they're under $10-20, they're definitely PWM. This one is the cheapest. The EA SunPower is the cheapest one I've been able to find that's a true MPPT. And you'll know it when you get it, because you can feel the copper inside, right? So in terms of operating voltage, I found that it's best to go with like a target voltage of 15.8, but you don't want to go any higher. So if you think, is this gonna burn out my head units or something, right, in my car? So all 12 volt automotive appliances, every electronic thing that's on the 12 volt system, it has to be rated for a lead acid battery environment. And we know that will typically charge up to like 14.5, maybe 15 volts. So it's called 12 volt, but it's really more like 15 volt every now and then. And in the Chevy Volt, we know everything regularly has to experience 15.5 volts. So that's kind of was my starting point. I read through the service manual and I found that the Chevy Volt doesn't really throw a high voltage code until the system gets to 16.1 volts. So that's for sure. Again, like higher voltage equals higher efficiency. And then we know solar panels are voltage specific, so that's really going to dictate the voltage of your system. So the thing with solar panels is they have a voltage open circuit, so like with no load attached, and then they also have something called a voltage maximum power, and that's basically the solar panel telling you, ideally I'd be charging at this, and you want your battery, whatever it's going to be charged to most of the time, to be like a couple volts under that. So like this panel would be slightly too high a voltage to use for a solar car application. You'd want something like 18 volts or maybe 16 volts. And then I didn't know where to put this, but I found car audio people on YouTube, people that are really into like, putting crazy subwoofers and stuff in their car. They have a lot of experience of tricking cars to run at slightly higher voltage because you get a little bit more power out of like your sound system. It's just kind of an aside I thought was really funny. You can basically the only people that are experimenting running higher voltage in their cars are car audio people, and they found LTO batteries, and they love them. But so yeah, here's some examples of lead-free Chevy Volts that are in current operation. There's my guy, which is like a LTO pack that I made, and then there's this guy in Russia. He started out using these, I think they're 10 amp hour cylindrical sodium ion cells in a 4S configuration, and then more recently he found these beefier 75 amp hour cells. So he, just for a point of reference, he lives in I guess a somewhat warmer part of Russia, if there is one, and then I live in the center of Washington. So if you need to know what temperature ranges these have been exposed to, these have been working for a couple of years now without issue. I guess that's kind of the end of my presentation. I got some random photos I threw in here. Not a lot of good photos of like the build process, but I guess I'll just say, like, the way I started is I just started buying stuff, and I started like putting it on my car and just kind of picturing things and measuring stuff out. How's it gonna work? Where are things gonna go? I think I see if I put it. I routed the solar panel wires through the antenna penetration here, and then so there's the headliner under there, and then they went over here through I think it's called the C pillar, and that's how I got into like the trunk and stuff to get to the low voltage battery. Now, it is worth pointing out, flexible solar panels, they're called that, but they're not really flexible, so I figured I had to add is called 3M window weld. It's a polyurethane based adhesive, but it doesn't cure like brittle. It stays kind of tacky, and it's really good at like gluing windows to cars. That's what it's made for. And it's kind of got like some thermal expansion so the glass doesn't crack. I found that stuff is like, it's perfect for adhering solar panels to cars. I don't know about removing it, but I mean, it comes off of cars when they take windows off. There's kind of a process you have to do to get it off, but theoretically it is possible to come off. I'm guessing it'll damage the paint, so just keep that in mind. You can always, if it damages the paint, you can always put another solar panel back on and cover it up, right? But I did find that I had to use kind of an extra amount over, I think, in this corner, basically to kind of make it more, make it less of a convex or a compound curve, make it less like a Pringle and more like a rainbow, right? So I think I used like one whole tube per panel, so that was not a insignificant amount of money. 3M makes good stuff, but it is expensive. And then here's another picture. I used, I need to find a better solution, but I used, it's called RV roof tape. It's the same stuff if you buy it from China. It's called butyl tape, I think. PVC coated butyl tape. And I just ran it around the perimeter to kind of give like a good transition for the laminar flow or whatever. And I mean, it looks okay. It kind of, it stays tacky forever, and that can like attract road grime. It's kind of hard to see. Oh, the box. So I started out with this 50 cal ammo can, and that was too tall. But I found these Plano shot shell boxes. I never seen anyone talk about these. They're like the same size but just shorter, and that actually worked really good. Drilled some holes for positive and negative, and then I made sure they're like super smooth, and I went over them with a lighter to like melt the plastic to make it really smooth. And then you're gonna need this curve if you do anything with LTO, like DIY battery. It's hard to find good information on LTO just because it's like a really niche chemistry. But you can see like above 2.5, 2.6 volts, the voltage just kind of hockey sticks up, right? So there's not really leaving anything on the table. It's my understanding there's like two manufacturers. The main one is Yinlong of LTO. They all come from China, of course. And Yinlong cells, they can go up to 2.9 volts and be okay. Ideally, you don't want to push them like past 2.8 volts. So I have to check the math, but I remember 15.8 volts is like the charging voltage. you're not really getting into that danger zone. So you're at like 90-95% state of charge utilization. And then if you're building a battery, it's super important. You got to top balance it like really good. So you get your cells, and then before you actually assemble it in series, what you do is you line it up all in parallel. And then so you basically make it one big battery. You connect all the positives and you connect all the negatives, and you charge it with like a power supply to like a kind of like a 80-90% charge. And then you move these leads around, and you do this over like a week. And essentially what that does is it makes the battery as equal as possible. Each cell is like, it's like one big battery. Because that voltage difference, when it ages, that voltage difference is only going to grow. So whatever you started at is, that's the key to long life. And then I hooked it in series. Oh, you want one of these? These are like a internal resistance. I mean, you don't need it, but it's basically lets you spy on the inside of the battery and see how messed up it is. I just bought one for peace of mind because these are coming from China, and I want to make sure like they didn't send me a bad cell. Apparently, if you get the cylindrical Yinlong cells, the 40 amp hour I think they're called, a lot of those are like from old recycled buses in China. So yeah, if they're suspiciously cheap and they're cylindrical 40 amp hour cells, you're definitely going to need one of these meters and check every one. But all of mine were basically, the way I knew they were okay is I noted the internal resistance. They're like, the low end was like 56 milliohms, at least how I was testing them, and then the high end was like 61 or 62. So they're all pretty much the same. You definitely don't want to do this with if there's like one is like twice of another one, right? And then this is the wrong balancer, but this is an inductive 6S active balancer, and I used it anyways. So yeah, that's my presentation. Thanks for coming on my TED Talk. Sorry if it was too long, and have a nice day.